Okay, today we will be talking about the so-called comparison tests, which will give you more tools for deciding whether series converge or diverge, and p-series, which is another class of series, another species, kind of like geometric series. We'll get to know those very well. And like geometric series, they also behave in a very simple manner. We'll start with comparison tests, but before we do, I should mention that comparison tests are specifically for positive series. What do I mean by that? I'm going to say that a series is positive if all of its terms are positive numbers. So for example, the harmonic series that we discussed last time is a positive series. Or this geometric series that we have referenced so often is a positive series because all of its terms are positive. But in fact, since we're talking about infinite series, and specifically about tests for convergence or divergence of infinite series, we have to remember that all we care about is the tail of the series, the infinite tail of the series, which is where convergence or divergence is determined. So when I say that a positive series is one whose terms are all positive, what I should really be saying are not positive series, but eventually positive series, meaning series that eventually become positive. So they might have some negative terms in the beginning, but they eventually become positive. If you go out far enough, you finally reach a region where, the rest of the terms are all positive. So it has a positive infinite tail, even if it has some negatives up front. It would get tiresome to say eventually positive series all the time, so I am just going to say positive series, and you should know that when we're talking about convergence or divergence, everything is determined in the tail. So if the tail is positive, the series is, for the purpose of a convergence test, a positive series. So if I threw in a -7 term in the beginning of this series, we will still call this a positive series because it has a positive tail. You might say, well, what if I threw a negative in, 100 terms down the road? Well, that's okay, because from the 101st on, it would be a positive series. You could stick trillions of negative terms in. It would still be a positive series as long as there are only a finite number of negatives, because as you march down the series, eventually you will reach the last negative, and everything after that will be positive. So it's an eventually positive series, so we'll just call that a positive series. Okay, all that is in the background. I mention it, as I said earlier, because these comparison tests, which I will introduce in a moment, apply only to positive series, by which I mean eventually positive series. And most of the series we will apply them to really will be strictly positive series. But it's good to bear in mind, and discussing this gives us yet another opportunity for emphasizing that convergence or divergence is something that happens in the infinite tail of a series. It has to do with whether or not the general term is vanishing fast enough as we go towards infinity. One reason we like positive series is that some of the weirdness that's possible with series doesn't happen with them. In particular, a positive series either converges, which we like, or if it diverges to infinity, like, for example, the harmonic series. You can't have something weird like the series 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus blah, blah, blah. This series diverges, as we've discussed before, but it diverges in a strange way. It doesn't diverge to infinity. Its partial sums just hop back and forth from 1, 0, 1, 0, 1, 0, and so on and so forth. It's an undignified kind of divergence, if you will. At least the harmonic series has the decency to ride off into the sunset of infinity, albeit slowly. It doesn't stick around forever. That sort of strangeness will never happen with a positive series for a fairly obvious reason. If our series is positive, then each successive partial sum, that running total that we keep, is going to be greater than the one before, because each term that we tack on just takes us further to the right. Now, there are only two possibilities. Either the thing just rides off into the sunset of infinity, or it doesn't. And if it doesn't go to infinity, then it's bounded by something. There's some wall that the series never gets past. That's what it means, after all, to be bounded, to not go to infinity. And if there's some wall that the sequence of partial sums will never get to, then since each step just takes us to the right, since we're just adding positive terms, we can never go backwards, and there are infinitely many of them, they are going to have to bunch up somewhere. Maybe they'll go all the way to this wall that I've drawn here arbitrarily, or maybe there's some point before that. and they're going to start bunching up close to that. Who knows? But anyway, the point is that positive series either has to converge or go to infinity. The partial sums can't start hopping around in weird ways, going left and right. But now let's actually get into our first comparison test. The first one we will discuss is called the direct comparison test for convergence. Let me give you the statement, and then I will explain why it holds. If the terms of a given positive series are always smaller than the corresponding terms of a known convergent series, then the given series must converge too. A bit of a mouthful perhaps, but I think writing it out in ordinary English actually makes it clearer than using symbols to describe it. You can see why it is called a comparison test. We have some given positive series that we're trying to test for convergence, and we compare it to some other series that is already known to be convergent. And if the two series stand in a certain relationship, we can conclude that our given series must converge too. Let me explain what's going on here intuitively, and then I'll show you an example or two of how we might put this into action. Let's say that our given series, the one that we are trying to test for convergence, is the sum of a sub n. So our general term is a sub n. Well, if we're using this direct comparison test for convergence, that means we must be comparing this to a known convergent series, which I'll describe as the sum of C sub n, C for convergent. When we are thinking about the theory of infinite series, it often helps to draw a kind of picture where each term, each of which is positive, can be thought of as the area of a particular rectangle. The widths are all 1, so the area of each rectangle is just equal to its height. That means the one here at 1, well, I can think of its area as being A1, and its area as being A2, and the area of this rectangle as being area A3, and so on all the way down to infinity. We can imagine partial sums on this as well. For example, the third partial sum would be the area of the first 3 rectangles combined. The full sum, the sum of the entire series, would be the area of all of the infinitely many rectangles all the way down to infinity, provided that area is finite. Now, of course, it need not be finite. If that area is infinite, that would mean that the series diverges. And so by thinking about areas in this way, a finite area corresponding to a convergent series or an infinite area corresponding to a divergent series, we can get geometric insight into what's going on with these tests. Here, for instance, we've got our given series. We don't know whether it converges or not. But we said if its terms, in other words, the areas of these rectangles, are always smaller than the corresponding terms of this known convergent series, then something happens. Well, let's think about that geometrically. If these are all smaller than the corresponding terms of this, in other words, A1 is less than C1, and A2 is less than C2, and A3 is less than C3, then the picture of the known convergent series would have to look something like this. The area of the first green rectangle would be C1. That includes the whole rectangle, not just the top part. The next one would be C2 and C3 and so on and so forth. And what do we know? We know that the green series, the convergent series, we know that it converges. So the area of that infinite staircase there is definitely finite. That's what it means for it to converge. But what does that tell us about the area of this other staircase, the one corresponding to our given series? Well, it must also be finite because it's contained within a finite area. So since it's finite, the series corresponding to it, the given series, must also converge, just as the direct convergence test tells us it will. It's one of the more intuitive tests for convergence we have, although I hope you'll see by the end that almost all of them are pretty intuitive if you just think about them the right way. Such is the direct comparison test for convergence. Let me give you an example or two of how we might use it. Let's test this series for convergence. This is not a geometric series, it's not the harmonic series, and the divergence test doesn't help us because as n goes to infinity, this denominator goes to infinity, which means that the whole general term goes to 0. And as we have said many times now, that's a necessary condition for convergence, but it is not sufficient. The divergence test can only be used to establish divergence. All right, so what do? We are going to use this direct comparison test. But to use a direct comparison test, we have to compare our given series with something else, one that we know already converges, and it's got to be a series that not only converges, but is related to this one in such a way that we can say that the terms of this one, like these guys right here, are always less than the terms of the one we'll be comparing it to. What series could we use? Well, think about the general term, 1 over 2 to the n plus 5. Ooh, it's that plus 5 that throws everything off. If only it were just plain old 1 over 2 to the n, because that one I recognize is a geometric series. Half plus a quarter plus an eighth, etc. That's a convergent geometric series. Maybe I can do a comparison test. For that to work, the general term of my given series would always have to be smaller than the general term of the series I want to compare it to. Is that the case here? Yes, it is. Think about the general terms. The difference is that in the given series, we've added 5 to the denominator. Well, when you add something to the denominator, you make the whole thing smaller. By making the denominator bigger, you make the entire fraction smaller. That means the general term up here is smaller than the general term of this known convergent series. Hallelujah, I've got it! The direct comparison test for convergence will work. So now let's forget about our scratch work and write it up a little more carefully. This series converges, but we're not stopping there because no one's interested in your opinion. We want to know why it converges. By direct comparison, so now we're writing down the test we're using, but direct comparison with what? With this series. Good, but how do we know that series converges? Well, we'll just write a phrase indicating how we know, which is a convergent geometric series with r equals a half. And now we have a complete explanation. Put that on your exam and you get a big check. Let's do another quick example. Let's test this series for convergence. Well, it's a funny looking series, and we could write out a few terms of it if you wanted to, but I'm not going to bother here. One thing we notice is that this n down here is a little pesky. If it were out of the picture, we would have the sum of 2/3 to the n. Well, that's a geometric series. Aha! Looks like a comparison might be in order. Will that work here? If I wanted to try to compare it to 2/3 to the n like that, will this work? I would need to know that these terms are always smaller than those terms. Is that going to be the case? Yes, it will, because we're always adding something to the denominator. We're adding something positive to the denominator because these are whole numbers. That means that the stuff up here is going to end up being smaller than the stuff down here. So I can write up my result more or less the same way. This converges by direct comparison with this series, a convergent geometric series with r equals 2/3. Easy as that. Now you might notice that in both the examples we did, we compared our given series to a convergent geometric series. You might say, will it always be with a geometric series? No. The problem is we don't have that many series in our toolkit yet. To use this test, we need known convergent series. And basically the only known convergent series we know at this point are geometric series. That will change by the end of this section because we will have some known convergent p-series as well. But we'll get to those in good time. I want to do a third example, or rather non-example. Let's test this series for convergence. Now you may be thinking, oh, I know what to do. This is kind of like the series whose general term is 1 over 4 to the n. Well, that's the same thing as 1/4 to the n. That's a convergent geometric series. We're in business. But we're not quite in business here. There's a problem. If this minus down here were a plus, we would be in business because 1 over 4 to the n plus n is indeed smaller than 1 over 4 to the n. But 1 over 4 to the n minus n, if we try to directly compare that to 1 over 4 to the n, we have a real problem. When we subtract n, we're subtracting a natural number from the denominator. We're making the denominator smaller, which makes the whole fraction bigger. So our given series has terms that aren't trapped below the terms of the known convergent series. They're riding up above it, which means that the direct comparison test for convergence does not help us in this case. So what do we do? Don't worry, we just need to wait for the limit comparison test. It will come to our rescue before the end of this lecture. But for now, there's nothing we can do with that problem, which is why I have cast it into oblivion. I'll rescue it again later. For now, what I want to do is move on to the next test. Instead of the direct comparison test for convergence, I want to look at the direct comparison test for divergence. And the test looks almost identical. I've erased a few words here, and we will fill them in together. Let's see if we can figure out, just by reasoning geometrically over here, what it ought to say. it's going to be a test for divergence. So it's going to be something in which we conclude that a given series diverges. So we're going to have to conclude that the area of this infinite staircase is in fact infinite. Well, what would let us conclude that that area is infinite? It would be infinite if it contained something that was infinite. Because there's no way for that something that is finite to contain something that is infinite. If a part of it has infinite area, then the whole has infinite area. So we would be looking for some known comparison series. Let's call it the sum of dn, d for divergent, some known divergent comparison series whose terms are always less than the terms of the corresponding given series. Aha, that would work. If this D series is known to diverge, then it would have an infinite area. Well, this bigger staircase contains the smaller staircase, so its area would have to be infinite as well, which means that the A series would have to diverge. And that's it. That's the insight. Now that we understand that, we should be able to fill in the blanks here and write down our direct comparison test for divergence. It's going to tell us that if the terms of a given positive series, our A series down here, are always greater than the corresponding terms of a known divergent series, our red D series, then the given series must diverge too. Pretty intuitive. Let's do an example. Let's test this series for convergence. That's kind of an interesting series. Let me come down here where I do my scratch work. It would look something like 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4 plus so on and so forth. What's that doing? I mean, it's definitely not geometric. The divergence test doesn't help me because as n goes to infinity, what happens to the general term? The denominator, square root of n, goes to infinity, which means that the whole thing vanishes. So that tells me nothing at all. Is this series going to converge? Is it going to diverge? Well, we think about it for a while, and we're thrown back to the idea of comparison. Maybe I can compare it to something I do know. It looks kind of like the harmonic series. If we could magically erase those square roots, it would be the harmonic series. And I might wonder, well, how does it compare to the harmonic series? I mean, I know the harmonic series diverges, but how do the individual terms compare with one another? Well, when you take the square root of a whole number, it of course gets smaller than that number. Square root of 2 is less than 2. Square root of 3 is less than 3. Square root of 4 is less than 4. But if you make the denominator smaller, you're making the whole fraction bigger. Hey, that means that this term is bigger than that one, and this term is bigger than that one, and this term is bigger than that one, and so on and so forth, all the way to infinity. Aha, that's exactly what we were looking for in the direct comparison test for divergence. Here's a divergent series, and here is a series whose terms are always riding above it. That means since this one goes to infinity, this one must go to infinity as well. That's it. But we don't stop here. We need to write up our solution so that others can follow our reasoning. This diverges by direct comparison. So you're stating the test with what series? With this series, the harmonic series, which diverges as everyone knows. And that's that. So now you have met the direct comparison tests. They're easy to understand, but they can sometimes be a little hard to put into practice because you have to juggle all those inequalities. Is this thing always greater than this? Is this thing always less than that? The examples we gave were fairly straightforward, but they could get ugly because you might have to actually prove that such and such is always less than the general term of some convergent series. We're not going to do anything too hairy in that direction, in part because we can often appeal to another kind of comparison test, which is called the limit comparison test. It might not be too surprising to see limits come into some sort of comparison test because convergence and divergence of a series are determined in the limit, in the tails of the series. Now, I think that in one sense, you will really like the limit comparison test because it's often easier to use than direct comparison. But in another sense, you might not like it as much because it's not as immediately obvious why it holds. Direct comparison, I hope those pictures we were drawing gave you a good feel for why they work. Limit comparison is also not too hard to understand, and I predict you will understand it, but I can't just draw a picture showing why it works. We have to really think a little more carefully about what an infinite series is. The reason why this limit comparison test holds will be much easier to understand, I think, if we take a minute at the beginning and discuss a simple idea that we'll need at the end of that argument. So, suppose we have a convergent infinite series. Quick question. If I make a new series, where I just take the old one and multiply every term by c, must this new series converge too? And the answer is yes. In fact, you saw in the last homework problem set, I think it was exercise 29, that you can take that series and simply pull the constant multiple through the summation sign, like that. This is very much like the sort of thing you did with the derivative operator or the integral, where in both cases you could take a constant multiple of a function and just pull it through the operator of interest. And it's pretty clear why you can do that here. Essentially, the idea is you're just factoring a c out of each of the infinitely many terms here. Instead of having this infinite sum, ca1 plus ca2 plus ca3 and so on, you factor that c out of all of them so that you have c times a1 plus a2 plus a3 and so on. So yes, if you start with a convergent series and you multiply every term by the same constant, the resulting series converges too. It will converge to c times whatever the original series converged to. Okay, nothing deep there. Let me ask a related question. Now suppose we have a series that diverges. Ask the same question. If I multiply all the terms by the same constant c, must the result also diverge? In general, the answer is yes, provided that c is not 0. That's a silly case, but that would actually flip it from divergent to convergent. But again, in such a ludicrous manner that it's not something we actually encounter. If we took, say, the harmonic series and multiplied every term by 0, well, then it would just be the series zeros plus 0 plus 0 plus 0 plus 0, which obviously converges. But for any other constant multiple, if the original series diverged, so will this new series. So if I started with the harmonic series and just decided to multiply every term by 18, it still diverges. It has to diverge. After all, if this thing somehow converged, then this result would apply, which means that we could pull the 18 through the summation and we would have this. But that doesn't make any sense at all, because of course we know that this is divergent. And this statement wouldn't make a bit of sense. I can't have a supposed convergent series equal to a divergent one. A convergent series, after all, is a number. A divergent series isn't anything. Even syntactically, the equal sign wouldn't make sense. So again, get rid of that, and we have that so long as we're not dealing with the silly case where c is 0, multiplying every term of a divergent series by the same constant doesn't change the convergent status. The result still diverges. And I want to sum all of this up in one little neat package. For any non-zero number c, these two series that we've been looking at stand or fall together, by which I mean either they both converge or they both diverge. Now there's nothing deep or surprising about this, but if I suddenly blurt it out in the midst of an argument, you might be left scratching your head for a minute. Having prepared the ground, when I need this fact in the argument that will justify this limit comparison test, which I'm about to introduce, it will all feel pretty natural, which is the goal here. Okay, it's time to state the limit comparison test. To test a given series for convergence, by which I mean its convergence status, convergence or divergence, we find a related series whose convergence status is already known. Now, what is meant by related will come out in a moment, but this is going to be our comparison series. So far, so familiar, but now we will see the difference. We look at the ratio of the general terms of the two series. If, in the limit, here's the limit in limit comparison test, this ratio of general terms approaches any non-zero number, it can be anything, just not 0, then the two series, the given series and the comparison series, stand or fall together, in the sense that either both converge or both diverge. And that is the statement of the limit comparison test. As with the direct comparison tests, I went out of my way in this video to state it without writing any symbols down, just in ordinary English. Even though it's a bit of a mouthful, I think it will help you understand what's going on. I've seen students get too hung up sometimes on the particular symbols involved, and they forget the ideas. So let's talk through this thing, get a feel for what it's actually saying, understand why it works, and then do some examples. But first, just on a very crude level, what is it saying? If I have some given series of terms of the form a sub n, I'll call it the A series, and I have some comparison series that sums up the Cn terms, where this is a convergent series. I'm not going to write down convergent, but the green for go and C for convergent should remind you. If I have such a setup, and I look at the ratio of the general terms, I pluck the general term off each, and I take the limit, and that limit is some non-zero number. Now remember, a limit might not exist, in which case the limit comparison test tells us nothing, or this limit might be 0, in which case the limit comparison test tells us nothing. But let's say this limit does exist and goes to some non-zero number. 22, let's say. It's non-zero. That means the limit comparison test would tell me that these two series stand or fall together. And since I already know this one converges, that would tell me this one converges too. Similarly, if I had some series and I compared it to some divergent series, maybe the harmonic series or something, and I did this with the limit comparison test, so I set up that ratio of general terms and take the limit, and what happens? Well, if it approaches some non-zero number, 66, then the limit comparison test would tell me that these two series stand or fall together. And since this one is already known to diverge, this one must diverge as well. That's all there is to it. Okay, so that's what it looks like in practice. We'll do a concrete example after we understand why it actually works. So why should this work? I can't just draw you a nice picture like I did with the direct comparison tests. But as I say, you can understand this one. Please don't just memorize it without understanding, because if you do, you're going to end up mixing up all these various tests we have. We don't have that many now, but we're going to build up some more. If you understand them, they're easy to remember. If you don't, they're not. So learn it well. Anyway, why is it true? So let's say our given series that we're testing is this series of A's, and the comparison series, whose convergence status we know, is this series of B's. Well, we take this ratio of general terms. We look at its limit as n goes to infinity, and we suppose that this limit is some non-zero number. Let's call that number, let's call it L for limit. The claim is that this should be enough to allow us to conclude that these two series stand or fall together. Why is that so? Well, it will be clear if we think about what this actually means. Don't just think about it as a process. First I do this, then I do this, then I take this thing, and if such and such happens, I get to write such and such on my test. No, what does it actually mean? If this ratio is approaching L, some non-zero number, that means that for large values of n, as we go deep out into the series, this ratio is approximately L when we are in the tail of the series, or tails of the two series, which matters to us because that's where convergence or divergence is determined. Let me rewrite this. Instead of saying when n is large, I'll just say in the tail of the series. When we go out into the tails of these series, this relationship holds, and it effectively becomes equality. But if this is true, well, let's just clear the fractions. A sub n is effectively equal to L times B sub n in the tails of the series. Maybe not when n is small, but go out far enough, go out to the billionth term of A, and you should find that A sub billion is just about L times B sub 1 billion. So in the tails of the two series, where convergence status is determined, the sum of A sub n is essentially the sum of L times B sub n. In other words, if we start summing at some sufficiently large number, start at 1 trillion or whatever, on each series, the terms in this series, once we go out that far, are each just basically L times whatever it was in this series. Might be very different back in the beginnings of the series, but go out far enough and that's the picture we'll see. And that's all we care about as far as convergence is concerned. You could chop off the first billion terms, the first billion terms, the first billion terms. It doesn't matter. That won't affect convergence or divergence. This series and this series are essentially the same thing in the tails. So since they're basically the same, those two series stand or fall together. But we also know that the latter series and the straight B series stand or fall together. So that means this one serves as a bridge between these other two. All three of them stand or fall together. And in particular, we can therefore conclude that the given A series and the comparison B series stand or fall together as claimed. And we are done. I hope that argument makes sense to you, not only because it will deepen your appreciation for and understanding of the limit comparison test, but it will help you think about infinite series themselves, and the crucial fact that convergence or divergence is determined in the tail of the series, and that so much of what we're doing is really aimed at what's going on deep down in the series, in the infinite portion of it. So if it made sense to you on the first time through, good for you, and if it didn't, come back to it after thinking about it a little more. You should be able to understand this one. Okay, that's why the limit comparison test works. Now let's actually put the thing to use in a few concrete examples. Let's test this series for convergence. I think this is the one I did a little while ago. It's hard for me to go back and check on the fly when I'm recording these things. Anyway, we saw something very much like this before, where I said, oh, if only this had been a plus, then we could use the direct comparison test, because every term in this is in fact less than every term in this series, and we know that this series converges because it's geometric with r equals 1/4, and that's less than 1. Well, if only, it isn't. So what are we going to do about it? Well, this is where the limit comparison test is very useful, because when I was talking about finding a related series, this is precisely the kind of thing I was thinking about, where you look at this and you think, what does this look more and more like as time goes by, as we go deeper and deeper into the series? 4 to the n is getting huge, but we're subtracting off n's, and those are getting increasingly huge, but 4 to the n grows a lot faster than minus n. I mean, this is exponential growth, and this is just linear decay. So this 4 to the n dominates in the denominator. When you have relatively small values of n, like 2, it makes itself felt. The denominator would be 16 minus 2, which is 14. You can feel that minus 2. But if this is 100, you have 4 to the 100th power, which is a gigantic number. I don't have my calculator with me, but 4 to the 100th, that's 2 squared to the 100, which is 2 to the 200, which is 2 to the 10th to the 20th power. 2 to the 10th is 1024, so that's bigger than 10 cubed, 1000 to the 20th power. That's 10 to the 60th power. That's a 1 followed by 60 zeros, and we're subtracting off a measly 100. It might as well not be there. As I say, this dominates over that, so that in the long run, this general term is effectively indistinguishable from the general term over here. And that's often how we're going to come up with the comparison series when we're using the limit comparison test. Like, well, what are the dominant aspects that really show up in the long run? And what are the insignificant things that just kind of fade away that we can forget about? And when we do that, we can take something kind of complex and clean it up into something simple. And since they're going to be roughly the same, we think, in the long run, well, shouldn't their ratio turn out to be, 1 or thereabouts? In which case the limit comparison test will help us, because 1 is non-zero, and that means the series would stand or fall together. And this one stands, it converges, so I think that means this should converge too. Let's check by carrying out the details. In fact, let me just continue my scratch work down here for a second before we write anything up formally. As I said, you do your scratch work somewhere, you work out what's going on, then you write it up nicely and turn that in. So let's think about this before we write anything down formally. We're thinking a limit comparison test might work here. Well, if I set up a ratio of the general terms, I would end up with something like 4 to the n over 4 to the n minus n. And what happens as n goes to infinity? That's just what we were talking about intuitively a second ago. This thing quickly pales into insignificance next to this. These, of course, are literally the same. So in the long run, this is going to look more and more like 4 to the n over 4 to the n, which is, of course, approaching 1. So now let's write this up cleanly, as you might on an exam or homework or whatever it might be. This series converges, why? By limit comparison with this other series. That's already half the battle because you've explained the broad outlines of why it converges. But let's apply a few more details. It converges with limit comparison by this. It converges by limit comparison with this. So we need to say why this one is convergent. A convergent geometric series. Good, now we know why that one converges. Even more specifically, where that ratio in absolute value is 1/4, which is less than 1, which is the condition for convergence in a geometric series. And let's see how that reads. The series converges by limit comparison with this convergent geometric series. Let's put the cherry on top. Since we want to know why this limit comparison test applies, if we take that ratio of general terms, we can rewrite it as a single fraction, and we recognize that that goes to 1 as n goes to infinity. And now we have a very thorough answer. We say what happens, the series converges. We say what test we used to conclude that by limit comparison. We compared it to what series? This one. Well, why does that series converge? Because it's a geometric series. How do I know it's a convergent geometric series? Because that common ratio is less than 1 in absolute value. And how did I know that limit comparison test applies in the first place? Because that ratio of general terms goes to 1, which I might even add is non-zero. Because the important thing isn't that it goes to 1, the important thing is that it goes to a non-zero number. And if you turn that in, I think your teacher will be very happy, especially if that teacher is me. Okay, that's the only example I'm going to give for now. I will return, I promise, and give another example of using this limit comparison test later, after we have spoken about p-series, because p-series will give us a much bigger stock of series with which we can compare series that we are testing. It gets kind of boring testing everything against geometric series, or I guess the harmonic series. So we shall see another example soon. So, p-series, what are they? P-series are relatives of the harmonic series. In fact, the harmonic series is one example of a p-series. A p-series is a series of this form, where we start with a harmonic series and we raise every term to the power of p, where p can be any real number. So when p is 1, we get the harmonic series. When p is 2, we get this p-series. The p-series when p is 18 is this series. Again, we're just taking the 18th power of every term in the harmonic series. And there's no need for p to be a whole number. We actually looked at another p-series already. When p is a half, our p-series is the sum of 1 over square root of n, which amounts to taking the square root of every term of the harmonic series. And we saw earlier in this video that this series diverges by direct comparison with the divergent harmonic series, because every term in this series is greater than the corresponding term in this series. Or, of course, we could have a p-series where p is pi. In that case, the series just looks like this. Well, I think you get the point, and you understand what a p-series is. What we want to do next is to investigate the convergence status of p-series. We know that sometimes p-series will diverge, obviously for the harmonic series, and we saw that this one diverges as well when p is a half. But what about these other ones? There are infinitely many values of p to investigate, so we have our work cut out for us. When the dust settles, though, and we have a definitive result about which values of p make this converge and which values of p make it diverge, we will be able to use p-series in comparison tests, both direct and the limit comparison test. And I'll show you some examples of how that works. That will greatly expand our possibilities for showing that other series converge or diverge. Recall that in the video on the harmonic series, we demonstrated the divergence of this thing essentially by comparing it to the area under the curve y equals 1 over x, which is of course related to the series whose general term is 1 over n. I'm going to do something similar with p-series in general, and we'll take it in pieces. I initially want to investigate the case where p is less than 1, kind of like this one, and then we will turn to the case where p is greater than 1, like any of these. But I want to remind you one more time, and approach it in a slightly different manner, about the dividing line here, where p is 1, where we have the harmonic series. And what I want to do is to draw the graph of the related function y equals 1 over x, the continuous version of this general term 1 over n. Now, I want you to remember from Calculus 2, or wherever you learned integral calculus, that the area under a curve over some infinite extent can be infinite or it can be finite. What was it in this case? Finite or infinite? Let's work it out really quickly. The integral of 1 over x from 1 to infinity, that's the logarithm of x, is the antiderivative as x goes from 1 to infinity. And we have to remember what this means. We're not really evaluating at infinity, strictly speaking. We're taking a limit as x goes to infinity. And what happens to the logarithm as x goes to infinity? It creeps slowly to infinity, but we still have to subtract what happens at the other side when x equals 1, log of 1, which of course everyone knows is 0, since 0 is the power you raise e to get 1. Well, infinity, so to speak, minus 0 is infinity. So this area is infinite. Now I'm going to jump over to GeoGebra and show you a little demonstration. hopefully give you a strong visual sense for what happens to a p-series in the case when p is less than 1. So I now pass the baton to the version of myself over at GeoGebra.
All right, we have now seen that the area under the graph of y equals 1 over x and to the right of that dashed line at x equals 1 is infinite, thanks to that improper integral we just computed. That fact lets us see that the harmonic series diverges very simply. If I were to put up rectangles representing the terms of the harmonic series in the usual way, they would look like this. The sum of the full harmonic series would be the total area of all those rectangles. And since the sum of all those rectangles clearly contains the infinite area underneath that curve, that sum must also be infinite. And hence, the harmonic series diverges, which we know already. Now, this is all preparatory to what I want to do with p-series. This blue curve, now lying on top of the curve we started with, is the graph of 1 over x to the p. And the reason why the two curves coincide right now is because I've set p equal to 1. But in fact, I have a little slider here, which will allow me to change the value of p and see how the graph changes as a result. For example, if I increase the value of p, let's increase it, say, to 2, we can see the graph coming down. There it is, where p equals 2. So the blue graph is now the graph of y equals 1 over x squared. And that happens, of course, if we keep going. If we push it up to y equals 1 over x cubed, or the 4th, or the 5th, by increasing the value of p, you're making the denominator get bigger and bigger, which makes the whole value get smaller and smaller and smaller. And the opposite happens if we move in the opposite direction. If we go back to where p equals 1 and then just keep drifting below 1, and we have p equals now 0.2, and we could even keep going past 0 if we'd liked. Or let's make it p is 1/2. So now the function, that pink function, is y equals 1 over square root of x. Well, we saw earlier that the sum of 1 over square root of n diverges by direct comparison with the harmonic series. And we can see that here too, because if I were to display the terms of that series, they would look like this. That first pink rectangle is 1. The second pink rectangle has area 1 over square root of 2. The third has 1 over square root of 3. The fourth has 1 over square root of 4, and so on and so forth. Those pink rectangles clearly have a total area that's infinite, because their area is even bigger than the area of our original rectangles, which corresponded to the harmonic series, which in turn are bigger than the area under the curve, which we saw was infinite when we computed that improper integral. And what I want to show you here is that there was nothing special about p being 1/2. Yeah, the p-series diverges when p is 1/2, but it also diverges when p is 0.7 for the exact same reason, or 0.9, or 0.3, or minus 0.2, or any value of p that is less than. This thing just varies continuously, and so long as p is under 1, the curve, and therefore all those rectangles, stay above that known divergent harmonic series. So any p-series where p is less than 1 will necessarily diverge by comparison with the old harmonic series. Okay, that's nice, but bring it back to 1. When p is 1, the p-series is the harmonic series, so of course it still diverges. But what if we take p higher than 1? Well, now the curve is on the other side, as are the rectangles. Does that mean we can conclude that the p-series will converge? Careful, we don't have enough information to say that yet. The fact that all the terms in the p-series in this case will be below the terms of the harmonic series don't tell us anything. The direct comparison test does not apply because we're not comparing it with a convergent series. We're comparing it with a divergent series. We can't conclude convergence. So we're going to have to investigate this separately. The divergence of the harmonic series doesn't tell us anything about the p-series when p is greater than 1. We're going to adapt the approach we have right here, but in a somewhat sneaky way. I'm going to jump back over to the blackboard and show you what I mean.
All right, so let's sum up what we know so far. We defined a p-series as any series of this form. We raise all the terms of the harmonic series to a fixed constant p. And we've seen that if p is less than 1, then the p-series diverges by direct comparison with the harmonic series, whose divergence we proved in an earlier lecture. So I guess strictly speaking, we should say that if p is less than or equal to 1, because when p is 1, the p-series is the harmonic series. But what about when p is greater than 1, when it's 2 or pi or 18? We shall see. But for now, we don't know. Well, let's investigate with the help of another picture. Here I have a graph representing y equals 1 over x to the p, where p is greater than 1. So it's going to be kind of like that graph of y equals 1 over x, but pulled down somewhat because of that greater power. Maybe only a little bit lower if p is just a bit greater than 1, maybe a lot if p is much greater than 1. But at any rate, this is the basic shape. Well, when we were playing with GeoGebra, I was drawing rectangles in such a way that their areas always exceeded the area under the curve by putting the curve up here at the upper left corner. But I want to do something different this time. Let's put them like this so that we have rectangles below this curve. So what would the areas of these rectangles be? Well, this one is evaluated at 2, so its height would be 1 over 2 to the p. So I'll write that in. And similarly, this one would be 1 over 3 to the p, and 1 over 4 to the p for the next one, and so on and so forth all the way down to infinity. And you might notice, hey, what about the first term? What about 1 over 1 to the p, which is 1? Didn't you forget this rectangle right here? Well, I'm going to leave it out because, once again, I'm going to be comparing these rectangles to the area under the curve, and I'd much rather deal with this stuff right here where I only have this one impropriety at infinity. I don't want to have to deal with this other asymptote as well. And it doesn't matter because we are investigating convergence, and we know that convergence status only depends on the tail of the series. Chopping off the first term won't change the fact that it converges or diverges. All right. So what I could say here is that the areas of all the rectangles will be my p-series, to be sure, where n is running from 2 to infinity. So that sum is going to be less than this improper integral, 1 over x to the p from 1 to infinity, since that corresponds to the area under the curve and to the right of x equals 1. Now, if this turns out to be finite, then we'll have that this infinite series is less than some finite number, which means that it must converge. So our hope is that this converges to something finite. This integral is more unpleasant in this general case where we have a p than it was when it was just 1 over x. So we have to be a little bit careful when we're thinking about it. It's going to be easier to deal with it if we think of it as x to the minus p, of course, because then we can integrate in the usual way, raise the exponent by 1, so that'll be to the power of 1 minus p, and divide by the new exponent. And of course, we are evaluating using the fundamental theorem of calculus at 1 and infinity, and we're going to do those subtractions. Now, the thing to bear in mind here is that p, the one thing we're assuming about p, is that it's greater than 1. That means that this exponent right here must be negative. So, when you raise x to a negative power, of course we could rewrite that as 1 over x to some positive power. And I'm not going to be any more specific than that. I'm just going to write this as 1 over x to some positive power. Now, that positive power happens to be p minus 1, but it doesn't matter. I think just thinking of it this way will help us see what is going to happen next. Sometimes too many details get in the way of understanding. All right, now all we have to do is evaluate this thing at the endpoints, the first of which, of course, is really a limit. So what happens when I pop infinity in there? Or in other words, I've got some fixed positive power, and I'm taking larger and larger values of x. What's happening to this whole thing as I do so? It might seem a little difficult to tell at first, just because there are so many different possibilities for this fixed exponent. I mean, if this positive power is 2, it's obvious. The bottom blows up to infinity, so the whole thing goes to 0. But maybe it's not so obvious what happens if this isn't 2 or 5 or 10 or something like that. What if this is just some really tiny positive power, like 1/1000th or something like that? Well, I think you'll be able to see that the same thing will still happen if we come over here and do a little numerical scratch work just to convince yourself. What did I say? X to the 0.001, 1/1000th? Fine. If that's my fixed positive number, a real small one, and I take huge values of x, is this whole thing still going to go to 0, just like if this were 2? Well, let's think about some extreme possibilities for x, both extreme to see what happens and convenient to make our numbers work out nicely. Let me take that decimal and rewrite it as a fraction. It'll be easier for me to follow my own work. Okay, that's better. If I want to convince myself that this is going to get close to 0, when x is really large, forget about a million and a billion and the kind of things I usually say. Let's dream up a huge value of x that will make this thing small. How about 1,000,000,000,000 raised to the 1,000th power? Good Lord, that's a big number. I picked that because these exponents will cancel with one another, leaving me with 1 over 1,000,000,000,000, which is, of course, very close to 0. And now I see what's going to happen. As gigantic as this number is, it's still pretty small compared to infinity. Every number is. And so if this is close to 0, it's going to get even closer as I drive this thing up to bigger powers. And so now I'm convinced that, yes, even if I have a very small positive power and I pop infinity in there, which sounds so simple, the whole thing is going to be vanishing. So that first term will be a 0. And then I have to subtract off the effect of putting 1 in there, which is, of course, just 1. So this turns out to be 1 over p minus 1. So what may I conclude? The sum of the p series for any p greater than 1 is going to be less than this finite value. That means that the p series is going to be less than this finite value. That's not going to be the sum of it, but the p series will be less than it. So the p series is finite. So the p series converges. What it converges to, I don't know, but I know that it converges. And you still might say, wait, you forgot about the case where n equals 1. You left out a term. Well, that's fine. If this thing converges and you throw in one extra term, you're just adding a finite number, 1, to some other finite number. So it's finite. So the whole series converges. That is, since this is finite, the p series converges. Hooray! We can now complete this sentence. When p is greater than 1 in a p series, the p series converges. And we now have a complete description of the behavior of p series. They converge when p is greater than 1 and diverge otherwise. This gives us many more series whose convergence status we already know. Those are series we can now use when we're doing comparison tests with other series that we don't know. For example, let's test this series for convergence. Oh my goodness, this thing might look intimidating at first. It's obviously not geometric. It's obviously not the harmonic series. Does the divergence test help me? No. This blows up to infinity, but the bottom blows up to infinity too, much faster, because I've got a 5th power here and only a cubic power here. So the whole thing goes to 0. So the divergence test tells me nothing. Am I going to do some kind of direct comparison? God knows with what. This is a complicated expression. I'd have to somehow prove that if I think it converges, that its general term is always going to be less than some convergent series, but what would that be? Eugh. Or does it diverge? I don't know. Well, I do know, and the key here is going to be the limit comparison test. I promised you I'd give you another example or two of it. And we are going to do a limit comparison with a p series. Let me talk you through this one to give you the intuition so that you would see this yourself. Anyway, let's think it through. On our first encounter with this, we're kind of knocked back on our heels for a second. But then, let's think about what these terms look like in the long run, because that's all that matters where convergence or divergence is concerned. What does the general term look more and more like in the long run, in the tail of the series? I asked a similar sort of question when we did that example of a limit comparison test before. Yes, the top is going to go to infinity. Yes, the bottom is going to go to infinity. But when n is a trillion, so that 5n cubed is 5 trillion, does that 15 really matter? It does not. Does that n even matter? No, not at all. It's getting blown out of the water by n cubed. And the same thing happens down here. For huge values of n, the 1 doesn't matter, the 7n doesn't matter, the 2n squared doesn't matter. Let's come down here and do a little scratch work. Shh, just between us. We won't turn this in, but this is how we're thinking. So for large n, the general term looks like this thing. We can just neglect those lower order terms. Oh, but when I see it that way, it doesn't look so bad because I get some cancellation, and that's just 5 over 6n squared. And then I remember something from the beginning of this video. Hey, wait a second. That series 5 over 6n squared, that stands or falls with the series 1 over n squared, because I can just take that constant multiple, 5/6, and move it out of the summation. Ah, so this guy in the tail looks like this guy, which stands or falls with this guy. So all three of those series should stand or fall together, which means that if I can prove that this one converges, which it obviously does, it's a convergent p-series with p equals 2, I should be able to conclude that this one converges as well. And the logic I'm using right here is the logic of a limit comparison test. So of course, I'm going to use my limit comparison test to get the job done. I'm going to do a limit comparison test with this guy. All right, I figured it out. I'll erase all my scratch work, except this, just as a quick reminder to myself while I am writing up my solution in a dignified manner. This series converges by limit comparison, I'm stating my test, with this series. I'll carry out the test in a second. Before I do, I'll note that this series is a convergent p-series, p equal 2, which is greater than 1. That's the condition for a convergent p-series. Okay, so where am I? This series converges by limit comparison with this guy since... Now I should give the actual details of the limit comparison test. How does it work? I need the ratio of the general term of my given series and the comparison series. So there's that ratio. Let's write it in a more sensible manner. The n squared comes upstairs and we have this stuff. Well, this is a rational function of n. All that matters is the highest power terms. So as n goes to infinity, we can neglect all that lower order stuff. This looks more and more like 5n to the fifth over 6n to the fifth. Those n to the fifths effectively cancel out, and this goes to 5/6. Now, why do I care about that? Because it's not 0, which means that the limit comparison test applies. And now I have a very thorough explanation of what happens. The series converges. I tell you the test I used to demonstrate it. I told you what the comparison series was. I told you why the comparison series converges. And then I explained why the limit comparison test itself applies. And that's that. So I hope that shows you how we can use p-series to carry out comparisons. And once again, how we might think about doing a limit comparison test. Let's do one last example. Let's test this series for convergence. Well, we stare at it for a few minutes. None of the obvious things that might dispose of it easily seem to work. And so much as when you learn to integrate, you're kind of thrown back. You have to think about it for a bit. And one of the typical things we will think about when that happens is, what does the general term look like in the long run? And we might say, oh, this plus n isn't really going to do anything in the long run. It just gets blown away by n to the 9th. So again, just thinking on my scratch paper, I might say, all right, well, that's kind of like the general term is sort of like this, which is 2n cubed. That's 9 halves power. Oh, that's not so bad. 3 is 6 halves, so that means there's 3 halves left over. I see. And now I have some insight into what's going on. The general term for large values of n is going to look kind of like this, 2 over n to the 3 halves power. And I know that the series like that stands or falls with this series because a constant multiple of all the terms doesn't change the convergence status. And this series is a convergent p-series because p is greater than 1. So now I have a really good reason to believe that this series is going to converge. But I have to nail it down. This is where I've gathered my intuition. Now I need to write it up nicely. Now I could try to do this with the limit comparison test, but I have a feeling it would get pretty ugly because of these square roots. So is there something simpler? Now that I know where I'm headed, now that I feel confident that this converges, I might think, well, is there a direct comparison I could do? Since the limit comparison would probably be nasty. And after thinking about it for a few seconds, you realize, oh yeah, there's an obvious direct comparison here. The general term of my series is always less than 2n cubed over square root of n to the 9th, which, as we were saying before, is the same thing as 2 over n to the 3 halves. And yeah, I can argue that that series converges directly. All right, so now I'm convinced not only that it converges, but that I can write up a direct comparison test to explain why. So let's do it. This series converges, why? By direct comparison with what? With this series, but how do I know it converges? Which converges because that series can be written this way, which can be written this way, and we know that that series converges since it is a p-series, with p equals 3 halves, which is greater than 1. That's the key to convergence of a p-series. And that's that. I want to mention one last thing before we go. As I've said a few times now, we're usually content with discovering whether a series converges or diverges. Actually finding the exact sum is usually not possible unless it's something simple like a geometric series. That's not to say that people don't try, though, and certain very special series that are not geometric, sometimes you can come up with exact sums. And it was an outstanding problem in mathematics for quite some time to try to determine the exact sum of the p-series when p is 2. It was known to be convergent, and you could add up a bunch of terms and get a pretty good approximation for what it converged to. But was there a nice expression for the exact value? Well, an answer was eventually found, once again, by our friend Euler, and Euler discovered that the sum of this series turns out to be, rather remarkably, pi squared over 6. How strange! How did pi get in there? What is this mysterious connection between this circular constant and squares? How he did that is too complicated to get into here. I will mention, though, that Euler found this problem sufficiently interesting that he went on to discover the exact value of the p-series when p is 4, and then when p is 6, and then eventually he was able to come up with a result that gave the exact value for the p-series for any even value of p whatsoever. But what about the odd ones? What about the simplest odd one for which it converges? We know this converges, but do we know the exact value for it? Euler was bashing out these results in the first half of the 18th century. Surely we've figured it out since then. We have not. Perhaps you are the next Euler and you can figure it out. I hope so. It would be nice to know what the sum of that series is. It was only in 1978 that it was proved that this number is definitely irrational. That was done by this fella, Roger Apéry. I don't know if that's how his last name is pronounced, but he did it in 1978. There is actually much more to the story of p-series, especially if you let p be a complex number. And once you do that, you are on your way to something called the Riemann zeta function, which is connected to a very important unsolved problem in mathematics called the Riemann hypothesis. This goes back, of course, to Riemann in the mid-19th century. It remains unsolved today, and if you can solve it, there is a $1 million prize for doing so. But before you crack the Riemann hypothesis, get those homework problems on comparison tests and p-series down.